All right, welcome back, AP Calculus. We're moving on to the next lesson. This is section 3.2. We're going to look at basic differentiation rules. So when we look at derivatives, when we did the limiting process, we were able to find the derivative of a function by taking a look at the limit. Well, in this lesson, we can kind of skip the limiting process. So we can skip doing the limit and just do the derivative using some algebra techniques, using some rules. There are some techniques to find the derivative, and that's what we're going to be doing today. So for example, before we get started, some labels for the derivative. So let's say you have your function y equals f of x. Let's say that's your function. Your function is f. That's supposed to be an f. Let me fix that for you guys. So let's say you have your function y equals f of x, and you find the derivative. Then a way of labeling the derivative is saying, you could say, give me one moment. Let's see if I can move this real quick. Just move this down a little bit. That way I can write the labels right underneath. And then move this little line. Could move that line. Alright. So the notation for derivative could be, there's different notations because calculus had different fathers. We had Newton and Leibniz, but we have f prime of x. That would be the derivative. Another notation would be f prime. That would be the derivative of f. Another notation would be dy dx. dy over dx. So we're taking the derivative of y with respect to x. Another notation would be the derivative of x of your f function. And lastly, one other notation that we don't really see would be capital D, derivative. Try that again, capital D, derivative of x of whatever function you have. In this case, we have our function is f of x. So these are the different notations in green of how to write the derivative. Okay, so now, and we're going to make the connection in a moment of the limit again and the derivative. We're going to make that connection when we get to power rule. So let's look at number one, the constant rule. So the constant rule means we have a line, we have a graph. So let's give you guys a graph. Let's say the graph is f of x equals 5. So that means we're gonna use we're gonna use this graph. So let's graph it. F of x equals 5. 1, 2, 3, 4, 5. So our graph passes through 5 on the y-axis, and that's our constant. Our constant is 5. So if we try to take the derivative, so let's write this down. The derivative ddx of the constant, in this case the constant is 5. The question is, what's the slope, right? What's the derivative of 5? Well, if you look at the green line, what's the slope of the green line? I'll give you a couple seconds to think. Hopefully you're thinking that the slope is 0 because the line doesn't increase. The green line doesn't decrease. So the derivative of 5 is 0. And that's the constant rule. When you have a line, a horizontal line, and you find the derivative of that horizontal line, in this case a number, a constant, any number, the derivative is 0. So that's the constant rule. Derivative of a constant is 0. And we can write that in words. Derivative of any constant is always 0. All right. And I guess we'll make one more notation for you guys right here. Slope is 0. And that's what we mean when we say derivative. We're talking about the slope. All right, the infamous power rule. So before we get to the power rule, I want to take you back a moment in time to what we did in the previous lessons and make the connection. I want to make you guys understand. I want to allow you guys to understand the connection between the limiting process and the derivative. So I think I have my tab here. Perfect. So here we're going to explore finding the derivative of some functions. In this case, the derivative we're going to explore is finding the derivative of x. And actually, I want to do something different just so I can differentiate these. Actually, no, that's fine. That's fine. We're going to find the derivative of x. In other words, f prime of x, yeah. Find the derivative, which is f prime of x. Just different ways of writing, right? So we got to find the derivative of x. Actually, I don't like this notation. I'm gonna erase this, sorry. This is not, that's kind of telling you something else. So I think like this, derivative of x. Take the derivative of x. So we're gonna approach this through the limiting process. So remember from chapter 2 we had the limit as h goes to 0. It was like the big formula. And actually, just so this stands out, let me write that in red. We had the limit as h goes to 0 of f of x plus h minus f of x all over h. Alright, so that's the formula we were using. That's one of the limit formulas. So if we use this formula for this derivative, right? This derivative that we're gonna have to find, then we know our function is f of x. Right? This is our function. F of x equals x. And we want to find if we plug in x plus h for x, right? If you plug in f of x into your function, you're gonna get, if you plug in x plus h into your function, you're also gonna get x plus h. Alright, so now we're gonna substitute those values into the limiting process, because the goal here is to find the derivative of f of x, of our function. So the derivative of your function is the limit as h approaches 0, x plus h, f of x plus h. We're just going to plug in x plus h because that's what we plugged in for x. And again, the x, this is what we're using. When we plug in x, you get x, check. When you plug in x plus h, you get x plus h. Minus x all over h. So at this point, we just do the subtraction. We know that the x's are going to cancel. So x minus x cancel. We can divide h. So h divided by h is 1. So the limit as h goes to 0 of 1 is 1. There's nowhere to plug in h, so your answer is 1. So we found the derivative of x, the slope of x is 1. Alright. as we continue exploring, this time, instead of derivative of x, we're going to say, what's the derivative of x squared? That's the question. What would be the slope function of the x squared graph? So using our limiting process again, if you want to find the derivative of this function, so we know our function is x squared, and we know f of x plus h, wherever you see an x, you plug in x plus h. So that's x plus h. Plug x plus h into the function and you get x plus h squared. That's f of x plus h. Now, since we have both cases, we can find the derivative. Limiting process, as h goes to 0, f of x plus h is this guy, minus f of x, which is x squared, all over h. Now, we've done these in the past where you have to expand and simplify out. So let's do this. Let's do it quickly. If you expand x plus h to the power of 2, you're going to get x squared plus 2xh plus h squared minus x squared all over h. Alright, can we cancel the x squares? And you're left with 2xh plus h squared on the top. We could certainly simplify that. By factoring out an h. Let's redo this guy here. Factoring out an h. And you get 2x plus h all over h. Here you could cancel out the h's. And do plug and chug. H approaches 0, so this guy goes to 0. And you're left with 2x. So now we know what the derivative of x squared is. The derivative is 2x. So I want you to hopefully try to see a pattern. There's something going on with the exponent. There's something going on with this exponent and this number in front of x. And when you take the derivative of that exponent, when you get your result, when you get your answer, there's a relationship between the original exponent and what you get in your answer. There's some type of relationship. Same thing with when you had derivative of x. I'm going to rewrite this real quick. When you had the derivative of x, we had derivative of x, but it had a power. The power is 1. So when you find the derivative, there's this relationship. Well, even though we got the answer of 1 as our answer, the derivative of x is 1, we could also say that there is a x and there is a power. X to the 0 power is 1. So if you don't see the pattern yet for the power rule, if you don't see the pattern yet, we're gonna do a couple. We're gonna do one more. Maybe that'll help you get the pattern. All right, so let's do one more. The derivative, the power rule. They call this the power rule because of the exponent, the power, x to the power of 3. Power of 3, x to the power of 3. So you want to find the derivative of that cube. So again, we know that f of x, our function, is x cubed, and f of x plus h is going to be x plus h cubed. Alright, now we're going to take that power, plug it into the limiting process to find the derivative, right? To find the derivative, that's the limiting process. And what we're finding when we take the derivative, and you know, it's good to hear it again and again. we're finding the instantaneous rate of change. Instantaneous. You know, we could find the rate of change given 2 points, right? That's the slope of the secant line. But to find the instantaneous rate of change, that's the slope of the tangent line. And this idea of it's not really possible to find the slope of the tangent line because you need 2 points to find a line. You need 2 points to determine a line. Rise over run, right? You need 2 points. But if you only have 1 point, 1 dot on your graph, then you're going to have to use calculus. And that's this idea of the limit, letting h approach 0. As h approaches 0. Alright. So we are going to start with a formula. It says f of x plus h goes first, minus f of x. F of x plus h is that cubic, minus f of x. And f of x, I did this too fast. F of x is x cubed. I'm not sure why I wrote x plus h. F of x is just x cubed all over h. Alright, let me fix this h too. Don't want to be sloppy with my writing. H approaches 0. Alright, so now we have this cubic that we have to take care of. So let's take care of that cubic. We have x plus h times x plus h times x plus h. We already know what this plus 2xh plus h squared. Bring down the x plus h. And now we're going to multiply the x first with every single term. So start with the x. You get x cubed plus 2x squared h plus xh squared. Now we're going to multiply the h with every single term plus x squared h plus 2x h squared plus h cubic. Then we stare at this and we see, can we combine anything? Okay, the x cubed itself, 2x squared h, can I combine? Yes, there's another x squared h, so that. Then there's xh squared, there's 2 of them, plus 1 more, that's 3x h squared. And lastly, there's that h cubed. So that is our cubic expanded. That's our cube expanded. So let's write that out. So when you expand, you'll get x cubed plus 3x squared h. And remember, we're still taking the limit of this. We have x cubed plus 3x squared h plus 3xh squared. And then there's a h cubed minus x cubed. The minus comes from the, remember we're subtracting f of x all over h. Alright, as you stare at this, think about what is it that you can still do. Hopefully you're seeing the minus x cubed and the plus x cubed. Cancel those terms. And at this point you could do butterfly method, which means every term that has an h can get divided by. So butterfly, this guy has an h. Those are going to cancel. Bam. This guy has 2 h's at the top. So those 2 h's cancel. And we can divide the last term by an h as well. The h cubed becomes a square. So if we were to clean this up, we still have the limit. As h goes to 0, we have 3x squared. The h's got divided out in the first term. We have 3xh. And lastly, we have plus h squared. At this point, we could do plug and chug. Let h go to 0. So once h goes to 0, this guy becomes 0, this guy becomes 0, and you take your limit, and your answer is 3x squared. That is your limit. That is the derivative of that cubic function. We started with x cubed, and the derivative was 3x squared. So feel free to pause the video to look at all the 3 cases and see if you can find a pattern, the power rule. See if you can find the power rule. What's going on to the power? What's going on to the exponent? What's happening to your function when you do the derivative? What is happening to your function when you go from function to the derivative? That's the question. Alright, so hopefully you're able to pause the video and see the pattern. So the idea is if you have some type of power, right? Let's say you have this function x to the 100, and you're asked to find the derivative. Then the 100 is your power. That's going to come to the front of your variable. You still have your variable, but you're going to do something to the exponent, to your power. And what you do is you subtract 1. Your power, you're going to subtract 1. So when you simplify that out, your derivative is x to the 99 power. So that's this idea of the power rule. The power goes to the front, you're going to subtract 1 to the power, and that end result is your derivative. And that's the connection between the limiting process. You saw that with the algebra. Now we're going to go back to our notes. And make sense of it. So the power rule says if you have x to some power, you can take that power, bring it to the front of your variable term, and you're going to have to subtract 1 to whatever power that is. That's the power rule. Okay. Something that we should know here is that n is any real number. Any real number. So don't think of n as another letter. Think of n as being a number. N for number. So for example, in the first example, you have x squared. We did that already in the previous right earlier. I showed you the limiting process. But if you find the derivative, take the power, bring it to the front, subtract 1. So it's just 2x. If you want to show the subtraction 1, you can, but I find that you don't need to. You could just subtract 1 in your brain. 2 minus 1 is 1, and that's an invisible 1. You don't need to put the invisible 1, but that is your derivative, 2x. Alright, next example, x to the power of 5. You go too fast, you might forget the dash. F dash, that's derivative. So the power. 5 goes to the front. Subtract 1 from 5, and you get 4. That's the derivative. Alright, next example, x to the power of 2/3. Now we're dealing with fractions, but it's the same thing. F prime. You're going to take the 2/3, that's the number, bring it to the front. Then you're going to have that 2/3 power, right? The 2/3, you still have it. But something happens to the 2/3. You're going to subtract 1. Okay, we have to always subtract 1 with your power. Now, if you subtract 1 from fraction, in order to subtract, you need a common denominator. So I'm going to make the denominators the same, 3/3. 3 divided by 3 is the same thing as 1. Let me make this in green so you see the connection. 3 divided by 3, that's 1. So now when I subtract, I get negative 1/3. Right? That's my subtraction answer when I subtract the fractions. But another way of writing that negative exponent is taking that x to the negative power and moving it to the denominator. When I move a negative power to the denominator, it becomes positive. So that's just another way of writing it. This is a just as correct as having the power on the denominator. You guys have to be comfortable with writing both situations, because on the AP test, they might simplify more, and this might be the multiple choice answer. But if you're doing the FRQ, the free response, and your answer happened to be a negative power, this would be okay as well. You wouldn't have to go the extra step. But just be comfortable with writing both. Alright, next example. So we want to find the derivative of 1 over x. So, here's your tip. Change to a power. How could you rewrite 1 over x as a power? Well, you could say 1 over x has a power of 1, invisible 1. And if you rewrite the fraction, you can make the power negative. Right? We just talked about making having a negative exponent. If it's on the top part of the fraction, move it to the bottom. If the power is positive on the bottom and you want to move it to have a power, just a regular power, move your variable term to the top. And that's how you get rid of that fraction. Alright, so we got rid of the fraction, now we have a power. Now we can do the derivative. So f prime of x, take the number negative 1, move it to the front, negative 1x, negative 1x, and subtract 1. Subtract 1 to the power. So I'm going to do that in green. Subtract 1. When you subtract 1 to negative 1, you get negative 2. Now that's our answer, but we could rewrite it, right? We could rewrite it as negative 1 over x squared. The x squared, the x squared had a negative power. It was x to the negative 2. But to rewrite the negative power, move it to the bottom of a fraction. The negative 1 was your number, so I just left it on top of the fraction. Alright, next example. So same thing, we have this fraction. We want to make that power negative. Think about how you could rewrite the fraction. X to the power of negative 6. Alright, now we're going to do the derivative. F prime of x. What happens to the number, the power? It goes to the front, right? So the negative 6 goes to the front. And you subtract 1 to the negative 6. So remember, we started with a negative 6, but we gotta... Oh, well, I wanna just emphasize something for you. We started with a negative 6, but you always gotta subtract 1 to the power. So negative 6x to the negative 7. And if I were to rewrite this one more time, negative 6 over x to the 7th power. Alright, in our next example, you have this crazy looking cube root with a x to the square. But you guys could do this, just breathe and think about how you could rewrite. So that's the tip here. The tip is rewriting. changing what they give you into something you know. So you know that you have an x squared. We have this x squared. But the cube root, you could rewrite the cube root as a fraction, as a 1/3. So something you need to know is if you had, let's write this in green. If you had a function, some function g, for example, and you had the cube root of x, that's the same thing as saying x to the 1/3. So I rewrote the cube root, and now I have two exponents. So using my properties of exponents, I could just multiply those out, and I get x to the 2/3. So that's my power. My function is x to the 2/3. Now if I do the derivative, the number goes to the front, subtract 1 from the power, which is subtracting 3/3, because I need a common denominator. And if you still have questions on this step, write the question down and make sure to ask me in class so I can help you out. Because this would be like a video question if you had a content question. So at this point, you subtract 2 minus 3, the numerators. 2 minus 3 is -1. And we have -1/3. So that exponent that's negative, I'm going to move it to the bottom of the fraction next to the 3. So the x goes with it. And that's what I get, 2/3 x to the 1/3. And if I wanted to, I could rewrite that one more time. I could say it's 2/3, and this is the cube root of x. This is the final simplified answer. The cube root of x is the same thing as saying x to the 1/3. Those two guys are the same. In math, we usually don't have, we don't show a negative exponent. That's just like one of the rules. Just like when you start a sentence, you always start with a capital letter. So in English, there's certain rules. Well, just like in English, there's rules to writing. In math, there's rules to writing as well. And so we don't like to have a negative exponent, and that's why we rewrite that. Alright, so we're down to our last two examples here with this power rule. So this is the square root of x. We're going to rewrite the square root of x as x to the 1/2. Go for it. You should try to move ahead of me. Let's do the derivative. F prime of x. What happens to the half? Goes to the front. What happens to the power? You subtract 1. So I'm subtracting 2/2 because I need a common denominator, right? I'm subtracting 1. So you get 1/2 x, 1 minus 2 on the top. 1 minus 2, that's -1. So that's your answer. But we need to have a positive exponent. So move the x term to the bottom. 1/2x to the half, which is the same thing as saying 1/2. Alright, I'm going to pause right here because I need to emphasize one thing. You're going to see this guy a lot. You're going to see it a lot. So that's one of the derivatives that it's like I encourage you to remember. Like, we just did the work to show you the answer, but I encourage you to remember, if you have radical x, and I ask you, I was trying to get the highlighter there. If you have rad x, and I say, what's the derivative of rad x? You need to know it's 1/2 rad x. 1/2 rad x. That's one of the derivatives that are common that you have to do quickly. Otherwise, all of this step is just gonna take you a long time to solve. I mean, it'll take you a couple seconds, but those seconds matter, especially if you're taking a time test. So again, if you have f of x equals rad x, and they say, what's the derivative? The derivative is 1/2 rad x. That's one of the common derivatives that you'll see pop up a lot in future problems. Alright, next example. F of x equals 1 over 5, 1 over the fifth root of x to the 6th. So we have the fifth root. Let's rewrite this. So I'm going to rewrite that as 1 over, we know it's x to the 6th power, because that's what we start with. But the fifth root is the same thing as saying 1 over 5. I'm going to multiply those exponents, and I get x to the 6 over 5. Then from there, I'm going to take my power and move it to the top. So that becomes a negative exponent, a negative power. Alright, so that's rewriting. Now, we do the derivative. So let's do this. Derivative. F prime of x. The number, the negative 6/5 goes to the front. You subtract 1. So I'm going to subtract 5 over 5. I need a common denominator. Subtract 5 over 5. So we have x. When you subtract 5 over 5, you have negative 11/5. That's a negative power. So I'm going to move that power to the bottom. Move the power to the bottom. Let me fix this 5 so it kind of looks nice. So we have 5. We have x to the 11/5. Alright, so that's our answer. It's a positive exponent. But we're just going to write this a little bit more, I guess, math appropriate. So let's continue right here. So you have negative 6 over 5. So we're taking the fifth root of x to the 11th power. That means we know we have x to the 11th power. That means we have 11 x terms inside the radicand. But every time you have 5 x's, those 5 x's are going to factor out. What I mean by that is, and I'll show you the step in case you need to see it. You have the fifth root, but you have 11 x's. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So these 5 x's, since you're taking the fifth root, are going to cancel. These 5 x's are also going to cancel. So your final result is negative 6 over 5x squared. You still have the fifth root because there's still 1x left inside. And that's your final answer for that derivative. We were using the power rule, but then we had this little algebra x to the 11/5 that we had to kind of clean up a little bit. We had the fifth root of x to the 11th that we had to like manipulate and clean up, and so this was our final answer. Alright, so we have now the constant multiple rule. So with derivatives, whenever you have a number in front of your function, you could deal with that number later. You don't have to deal with it right away. What I mean by that is, let's say you want to find the derivative of your function. You want to find f prime. Well, what we're saying is find the derivative of your function. Right? Your function is 6x to the 4th power. But that 6 number, the number 6, you could deal with it later. The constant, you could move it to the front. And just do the derivative of x to the 4th. Just do the derivative of x to the 4th. So you have the 6. When you do the power rule, And now when you do the multiplication, 6 times 4 is 24, and you still have x cubed. So that's using this constant and then multiply the derivative rule. If you wanted to do power rule right away, you could have. There was nothing stopping you. If you chose to do power rule, you would be multiplying the 4 and the 6, right? 4 times 6 is 24. Subtract 1 from the power. So there's just different ways to get the derivative. Alright, in the next example, we have 5x cubed. So same idea. Find the derivative. You could have that number, treat that number like, multiply that number later, and just do the derivative of x cubed. So you're gonna leave the constant alone till the very end. Derivative of x cubed is 3x squared. 3x squared. And 5 times 3 is 15, x squared. So that's all we're saying. You could multiply the constant in later on. But you didn't have to. You could have just went straight to the derivative using power rule. 5 times 3, 15. And subtract 1 from the exponent and you get x squared. Alright, our next example. Now we have this fraction, but it's the same idea of the constant multiple rule. F prime of x, the derivative. Multiply that negative 3 and later. Just do the derivative of that power. So f prime of x, if you do the derivative of that power, you're going to get 2/5. The power goes to the front. You're going to subtract 1 from 2/5. So if you subtract 1 from 2/5, you're really subtracting 5/5. Subtracting 1, which means you're really subtracting 5/5. And you're going to end up with x to the power of negative 3/5. And we have a negative power. So we could move the power to the bottom. And it's x to the 5th power. Well, let's write it like this, 3/5. There's a lot of little algebra things that we could do here. Alright, now we're going to multiply the numbers, the negative 3 and the 2. So you get negative 6. On the bottom we have a 5. But you also have x to the 3/5. Okay, so x to the power of 3 over 5. So this is actually x to the 3rd power, but you have the 5th root. That's a 5. Alright, so this is a 5. The 5th root. There you go. So 3/5 is x to the 3rd power over 5, which is the 5th root. And that's your final answer for that derivative problem. Alright, we got 2 more. Next example, f of x equals 2 the 4th root of x cubed. So as I see this, I'm thinking, okay, let's change the look. Let's change how this looks. So what we're gonna do is keep the cube, x to the 3rd power, but put the 4 on the bottom because it's the 4th root. Just looking at some of my examples here. Constant multiple rule, nice, okay. So at this point, when we do the derivative, since we're still talking about constant multiple rule, we could leave the 2 out for, oh yeah, we could leave the 2 out for later. So right now, we're going to do the derivative. This is f prime. 2 derivative of x to the 3/4. So when you take the derivative of a power, that power goes to the front. So I'm going to get 3/4 x. Subtract 1 from 3/4. Subtract 1. Let's see if we can do that in our brain. Subtract 1 from 3/4, which means subtract 4 over 4, which gives me, it's going to give you negative 1/4. You could simplify these guys. You get 1/2. So you end up with 3x to the negative 1/4 all over 2. And you could put that negative power on the bottom, and you get x to the 1/4. That's supposed to be a 4. And you could rewrite that as with a root, so the 4th root of x. Alright, our last example for these types of problems, before we get into our last 2 examples, we're almost done, you guys, is 4 divided by the 6th root of x. So again, what I recommend for you, since we're learning about power rule, is turn these into powers. So I'll rewrite into something you know. So let's start rewriting. What do we know? Well, how can we rewrite this? Well, that 6th root of x, you could write it as a power, since we're learning about power rule, x to the 1/6. Then let's get rid of the fraction by moving the x variable term to the top. So your function becomes 4x to the negative 1/6. When you move a variable between the bottom or top of a fraction, you have to change the sign. So now that we used algebra to change up how our function looks, now we're going to find the derivative, f prime. Again, you could use the constant multiple rule. Let's see. This is called the constant multiple rule. Or you could use power rule, right? You have a choice. The 4, you could deal with it later since that's the constant, or you just multiply right away. So this is just regular, good old-fashioned power rule. Multiply the 4 with the negative 1/6. That's power rule. The negative 1/6 goes to the front. Then you're going to subtract 1 from the negative 1/6. So when I multiply negative 1/6 with the 4, I could simplify before I multiply. Maybe that'll help this easier. Maybe clean it up, or maybe make an easier problem. So simplify by 2. This becomes a 2. This becomes a 3. So I end up having negative 2/3. Negative 2 over 3. Because 2 times negative 1 is negative 2. Then, when I subtract negative 1/6 with 1, I'm really subtracting 6 over 6. Common denominator. So my final answer is negative x to the power of negative 7, 6. But remember about those negative signs, the powers, you want to make them positive. So we're going to bring the variable to the bottom. And you have a power 7, 6. So we can rewrite as much as possible. So we have x to the 7th power, and this is the 6th root. Now I want you to think about how you can simplify that. You have the 6th root of x to the 7th power. So what that means is, if you have 6 x's inside the radicand, one of the x's could come out. And one of the x's is still left over, and we still have the 6th root. So that's the final answer of that derivative. And again, you have options. You could use power rule, or you could use the constant multiple rule. These are our last two examples, ladies and gentlemen. Kind of like putting these ideas together. When you do the derivatives, it could be a polynomial. It doesn't just have to be like one term function. And this is this idea of the sum and difference rule. What the sum and difference rule is saying is you could do a derivative of multiple functions of a polynomial, basically. So when you do that, when you do the derivative of f, it'll be the derivative of f plus or minus the derivative of a g function. Get carried away with my parentheses here. Derivative of g. So you could do the derivative separately. So let's see how that looks in this example. F of x equals the 6x cubed minus 3x plus 4. When you do the derivative of f of x, power rule, 6 times 3, 6, 12, 18. Subtract 1. That was a bad 18, sorry. 18. Subtract 1, you get x squared. Derivative of a negative 3x. What's the slope of this guy? If you had an equation y equals negative 3x, the slope is just negative 3. And the derivative of a constant, we learned that in the first example, was just 0. So that is our answer. Alright, in our next example, f prime of x. So we want to find the derivative of that. The first term, so that 7 multiplies with negative 3. You get negative 21 x, subtract 1 from 7, and you get a 6. Alright, here, let's rewrite this so that way we can take the derivative. So I'm going to rewrite this over here. It's going to be 2 over x to the 1/2, which becomes 2x to the negative 1/2. So when I do the derivative of that fraction, I'm really doing the derivative of the power. So the negative 1/2 is going to multiply with the 2 when I do the derivative. Using power rule, I'm using power rule. So maybe I could show you on the side. I'm taking the derivative of 2x to the negative 1/2. So what I know is that that power has to multiply with the 2. So what's half of 2? That's 1. But because I have a negative half, it's going to be negative 1. So this is negative 1. Then I have x. And when I subtract 1 from that power, the power is negative 1/2. When I subtract 1, I'm going to end up with negative 3/2. And the derivative of a constant is 0. Now if I clean this up just a little bit, I get f prime of x equals negative 21x to the 6 minus 1. I'm going to put the x term on the bottom. And I can clean this up just a little bit more. Negative 21x to the 6 minus 1 over x cubed. So the square root of x cubed. And if I clean this up just one more time, you're going to see that since there's 3 x's inside the radicand and I'm taking the square root, one of the x's could come out. Well, not one, I mean like there's 2 x's inside that get square rooted. So 1x comes out, and inside you still have 1x left over. Remember, here we have 3x's. We're taking the square root, so 2 of the x's inside cancel, and that becomes x with 1x inside. Alright, that is the final result. Maybe a question you have is, do you have to write this 2? No, you don't. If you don't write the 2, we know it's a square root. So you could have easily said the answer was negative 21 x to the 6 minus 1 over x square root of x. That is fine as well. Alright, so your homework is page 136, numbers 3 through 38. And this is the lesson on derivatives, basic differentiation rules. Thank you guys for tuning in. Take care.